Good morning, everyone. Today I am going to present my topic. My name is Sakshi Mohite. My roll number is 4012, and my topic is object-based architecture and mutual exclusion algorithms. So, in concurrent system, multiple processes on threads may try to access the same shared resources at the same time. This can create problems such as race condition and inconsistent data. So in this presentation, I will first explain object-based architecture, then the mutual exclusion problem, followed by Peterson algorithm, Bakery algorithm, and finally hardware-based synchronization using test and set. So let's start with object-based architecture. Object-based architecture is a way of a system where data and the operation performed on that data are grouped together inside objects. There are three important concepts here. First is encapsulation. Encap- Encapsulation means the internal details of an object are hidden, so other components uh, don't need to know how everything works internally. So show only essential data which is required. So second is interfaces. Communicate with each other through well-defined interfaces, and this reduces unnecessary dependency between components. Third is modularity. The system is divided into smaller parts and manageable components, so which make concurrent system easier to maintain, understand, and test. So object-based architecture help us organize complex systems in a cleaner way. So uh, next is the mutual exclusion problem. So now let's understand the mutual exclusion problem. When multiple threads access a shared resources simultaneously problem can occur. So for example, imagine two people trying to update the same bank account at exactly the same time. If both transactions read and modify the balance simultaneously, the final result may become incorrect. So this is called a race condition. And to avoid this problem, we use mutual exclusion. So mutual exclusion means that only one thread or process should execute the critical section at a time. So a critical section is the part of program where shared resources is accessed or modified. So the main goal is to make sure that two processes don't enter the critical section simultaneously. Peterson. So next is Peterson algorithm. The first solution we will discuss is Peterson algorithm. Peterson algorithm is a classic software-based solution for two processes and does not require special hardware support. So it mainly uses two things, a flag array and turn variable. So the flag tells us whether a process wants to enter at the same time. The basic idea is simple. A process first sets its flag equals to true, and which means I want to enter. So then it gives the turn to the enter to the process. So if processes are trying to enter, the turn variable helps decide who should wait. So in this way, only one process enters the critical section at a time, and Peterson algorithm provides mutual exclusion and is designed to avoid deadlock while allowing processes to eventually enter the critical section. So this is the Peterson algorithm. This is the code example. Let's look at the code. First, flags equals to I equals to flag of I equals to true. So as I said earlier, that means process I wants to enter critical section. Then turn equals to J means process I give priority to the in other processes. So the while condition checks whether the other process also wants to enter and whether it currently has the turn. If that condition is true, the process waits. And once the condition becomes false, process enters the critical section. After completing the critical section, it sets flag of I equals to false. So we can remember Peterson algorithm using 5 steps: flag, turn, wait, critical section, and release. Next is bakery algorithm. This is the easiest way to understand this algorithm and compare it with real bakery. Imagine when we enter a bakery and take a token number. The person with smaller token number gets served first. And the bakery algorithm works in a similar way. Each process takes a ticket number before entering the critical section. Then waits for processes with lower ticket numbers to finish. If two processes receive the same number, their process IDs are used to decide the order. Then the important advantage is that the bakery algorithm can handle multiple processes, unlike Peterson algorithm, which is designed for two processes. It also provides fairness because of processes enter according to ticket order. So let's see code example. Here is the step-by-step logic also, and now the code is first, the process takes the next available ticket number. Then it checks tickets, ticket numbers of that of other processes. Then, if another process has a lower priority, the current process waits. The comparison of ticket number and process ID is used to decide which process should enter first. So, after entering and completing the critical section, the process resets its ticket number to 0. So simple flow is take a ticket, compare, wait, enter the critical section and reset the ticket. So next is a hardware support, test and set. One important hardware primitive is called a test and set. So test and set performs reading and writing of a log. It's a single atomic operation. So that this means the operation cannot be interrupted in the middle. A simple technique like can continuously check the log until the process successfully acquires it. Then the advantages is that uh, the advantages of the hardware support is it is that can be very efficient when there is a low congestion. However, uh, when many processes compete for the same log, it can cause catch line congestion and additional bus traffic. So it is fast in some situation, but not for it not always the best choice under heavy congestion. So here is a practical consideration. Now let's compare the different approaches. Peterson and Bakery algorithm are software based and do not require special hardware. They are useful for understanding the fundamental concept of synchronization, but they can have overhead because of busy. So hardware primitives such as test and set and compare and swap are faster and simpler, but their scalability can suffer many processes when many processes compete for the same resource. In modern system, hardware primitives are usually combined with operating system mechanisms such as mutex, simpros, and condition variable. So that's it. Thank you.